Hi, I am RVC Triambulo from BS Ed Math 3A. And now I am going to share with you about the emergence of American mathematics from the transition to the 20th century to Cantor and Kronecker. So now let's talk about first the ascendancy of the German universities. So at the time of Prussia's deepest national despair, a new university was founded in Berlin. The new university was intended primarily to develop knowledge, secondarily and perhaps as a concession. It was to train the professional class. As the 1800s advanced or 18th century advanced, other universities were found on the new model of Berlin. The German universities, with their combination of lectures, seminars, and laboratory, were felt to be about the only institution in the world where students could obtain training on how to do scientific and scholarly research. In the 19th century, the German university was the most admired university of higher education in the Western world. Second, let's proceed to the American mathematics takes root. So as the 18th century drew to a close, mathematics was the only state of rapid change. New areas of mathematics remain wide open to research, while older, established areas of mathematics were finding new applications. Advances in analytic geometry, differential geometry, and algebra all played important roles in the development of mathematics in the 18th century. Building upon the mathematical work of the 18th century and developing new areas of mathematics previously unknown, the 19th century witnessed some of the greatest discoveries in mathematics since Euclid and ancient Greeks. After many changes in mathematics, there is a new discoveries in math. Mathematics became required knowledge for the educated person who is interested in keeping up with the flurry of changes in the world. Now let's proceed to the 20th century consolidation. The 20th century continued the trend of the 19th century towards increasing generalization and abstraction in mathematics, in which the notion of axioms as self-evident truths was largely discarded in favor of the emphasis on such logical concepts and consistency and completeness. Mathematics became a major profession involving thousands of new PhDs each year and jobs in both teaching and industry, and the development of hundreds of specialized areas and fields of study such as group theory, knot theory, shaft theory, graph theory, functional analysis, singularity theory, catastrophe theory, case theory, model theory, category theory, game theory, complexity theory, and many more. And I just want also to share with you that in 20th century, Mr. Grothendieck is the greatest mathematical 20th century. He transformed thinking about spaces and numbers by his work in the field of algebraic geometry. And I just want to share also with you that Mr. Grothendieck is the greatest mathematical in the time of 20th century. He transformed thinking about spaces and numbers by his work in the field of algebraic geometry. Now let's proceed to the last universalist, Poincare. Poincaré often described as polymath and in mathematics as the last universalist since he excelled in all fields of the discipline and it existed during his lifetime. Poincaré was the first to introduce four vectors, the Lorentz groups and its morions, including the space-time metric. Poincaré stresses, as well as making other valuable contributions and relativity theory. Jules Henry Poincaré made a series of profound innovations in geometry, the theory of differential equations, electromagnetism, topology, and the philosophy of mathematics. Next is the Cantor's theory of infinite sets. Cantor's theory implies that there are sets having cardinality greater than the infinite cardinality of the sets of natural numbers. Cantor's theorem for infinite sets rested on the version of his called diagonalization argument, which he had earlier used to prove that the cardinality of the rational numbers is the same as the cardinality of the integers by putting them into a one-to-one correspondence. Infinite set is a set that is not literally not a finite set. Infinite set, it is also called uncountable set. Cantor established the importance of one-to-one correspondence between the numbers of two sets, defined infinite and well-ordered sets, and proved that the real numbers are more numerous than the natural numbers. Now let's go to Kronecker view of set theory. Kronecker believed that mathematics should deal only with finite numbers and with finite numbers of operation. Kronecker was primarily an arithmetician and algebraist. His major contributions were analytic functions, the theory of algebraic equation, and the theory of algebraic numbers. Kronecker criticized Cantor's work on set theory. Led by Leopold Kronecker, an entire school of thought opposed Cantor's abstractions. Because Cantor's ideas pushed the boundaries of mathematics and were often counterintuitive, their mathematical importance and even validity come under intense scrutiny. Countable and uncountable set. Countable means we can able to count the people or the number. It is countable if the set has the same cardinality. It is capable of being put into one-to-one correspondence with the positive integers of countable set. A countable set is either finite or countably infinite. But please take note that all finite sets are countable, but not all countable sets are finite sets. Now let's proceed to uncountable sets. It is infinite set that contains too many elements to be countable. It cannot be put into one-to-one correspondence unlike the countable sets. Uncountable means we can't able to count it because there are too many or the number is too large. Thank you so much for listening, and my partner will continue to share with you about the history of mathematics.
Good day, everyone. Today we're going to discuss the transcendental numbers. For the moment, we have been considering a division of real numbers into two subsets, those that are rational and those that are not. It is also possible to think of another partition of real numbers into those that are roots of equation and those that are not. We have definition here. A number, real or complex, is said to be an algebraic number if and only if the root of the algebraic equation a sub 0 x to the power of n plus a sub 1 x to the power of n negative 1 plus a sub n negative 1 x plus a sub n is equals to 0, where a sub 0 is not the element, where n is a natural numbers and each a sub I is an integer. Any rational number is algebraic. If R is rational number, say R S over T, where S and T are integers, then R is the solution of the equation Tx minus S is equals to 0. On the other hand, not all algebraic numbers are rational. The irrational numbers square root of 2 is algebraic because it is a solution of x squared minus x is equals to 0, similarly to 1 half cube root of 3 as root of equation 8x cubed minus 3 is equals to 0 is an algebraic number. Let us use the letter A to denote the set of algebraic numbers. Then, in the hierarchy of subset of real numbers, where we have an ascending chain set, Z subset of Q, subset of A, and subset of R. The question naturally arises whether the set A constitutes the totality of all numbers, or whether there are real numbers that are not algebraic. Such numbers are called the transcendental. For Euler said, they transcend the power of algebraic methods. Euler was one of the first conjectures the existence of transcendental numbers. Just it was by no means obvious the irrational number exists, so it was no means obvious the transcendental numbers exist. No satisfactory answer to the questions of their existence was found until 1844, when the great French analyst Joseph Louisville obtained a whole class of such numbers, namely those defined by infinite series summation of infinite a sub n 10 to the power of negative n factorial, where n is equals to 1, where each a n is the arbitrary integers between 1 and 9. We have a is equals to 10 to the power of negative 1 plus 10 to the power of negative 2 plus 10 to the power of negative 6 plus 10 to the power of negative 24 plus 10 to the power of 120, and so on. So we have a is equals to 0.11. The proof of their hierarchy, the proof of their transcendence was eventually set for 1851 by Louisville on his own periodical Journal des Mathématiques in a memoir under the title On a Very Extensive Class of Quantities which are neither algebraic nor reducible to algebraic irrationals. For quite the time, Louisville transcendental number were the only one known. This situation changed radically when Cantor, in his 1874 paper, used relatively simple set theoretic method is to show that almost all real numbers are transcendental, not algebraic. To develop the proof of the countability of the set of algebraic numbers, we begin by considering an arbitrary algebraic equation a sub 0 x to the power of n plus a sub 1 x to the power of n negative 1 plus a sub n negative 1 x plus a sub n is equals to 0, where a sub 0, a sub 1, and a sub n are integers and a sub 0 is greater than 0. The height of this equation is defined to be the integer. So we have h is equals to n plus a sub 0 plus a absolute of a sub 1 plus absolute of a sub n minus 1 plus a sub n. Because the integer a sub 0 and n are at least 1, the height h is greater than equal to. We have 3x squared minus 2x plus 1 is equals to 0. So h is equals to 2 plus 3 plus 2 plus 1 is equals to 8. For any fixed height or h, the integers n, a sub 0, a sub 1, a sub n negative 1, a sub n can be specified only in a finite number ways, thereby leading to finite numbers of equation. Each such can have at most as many different roots as its degree. When an equation's height is 2, we have n is equals to a sub 1 is equals to 1 and a sub 1 is equals to 0, so that the equation must be x is equals to 0. Then 0 is the sole root of this equation, hence the first algebraic numbers. We shall be explicit about the one more step by considering equation that satisfy the condition n plus a sub 0 plus absolute a sub 1 plus absolute a sub n is equals to 4. There are various possible as listed here. We have the equation, we have the following equation and the roots. The x positive negative 2 is equals to 0 is its root is positive negative 2. We have 2x positive negative 1 is equals to positive negative 1 half. We have 3x is equals to 0 when roots is 0. We have x squared plus positive negative x is equals to 0, then roots is 0, positive negative 1. X squared positive negative 1 is equals to 0 and roots is positive negative 1 or positive negative I. 2x squared is equals to 0, roots is 0, x cubed x cubed is equals to 0, then the roots is 0. The following sequence of algebraic numbers, we have 0, negative 1, 1, negative 2, 2, negative 1 half, 1 half, negative 3, 3, negative 1 third, then 1 third, positive 1 third, negative square root of 2, then positive square root of 2, negative square root of 2 over 2, and positive square root of 2 and 2. An algebraic number is a root of an algebraic equation, and every such equation has a height. We cannot miss any algebraic numbers with this scheme. Thus, our argument proves a theorem. We have a theorem. The set A of real algebraic numbers is countable. The set T is transcendental numbers is uncountable. The set of real numbers R is equals to A union T. If it happened that T were countable, then R is the union of countable set that would itself be countable set. Cantor's proof of uncountability of the transcendental has only theoretical character and is not of much use in determining which certain specific number are actually transcendental. The problem of the transcendental of the classical constant E and pi attracted mathematicians as soon as Louisville had justified the distinction between algebraic and transcendental numbers, because the number E or D, Euler, and pi are closely connected by the Euler equation e to the power of pi sub I plus 1 is equals to 0. The investigation of their nature was carried on at much the same time. The irrationality of E or Eulerian has been demonstrated earlier by Euler in 1737, published in 1744. Louisville had shown in 1940 that neither E could be a root of the quadratic equation with integral coefficient. Within a decade, Ferdinand Lindemann was able to confirm in an article über die Zahl pi that pi is transcendental modeling of his proof on Hermits. Lindemann argument required the theorem for that any distinct algebraic number a sub 1, a sub 2, a sub n, real or complex, and any non-zero algebraic numbers beta sub 1, beta sub 2, and beta sub n, the expression beta sub 1 Eulerian to the power of a sub 1 plus beta sub 2 Eulerian a to the power of a sub 2 t plus beta sub n Eulerian to the power of a sub n must always be non-zero. Complex number I is a root of the equation x squared plus 1 is equals to 0 is algebraic, and since e to the power of pi sub I plus e to the power of 0 is equals to 0, it follows that the number of pi I and therefore pi cannot be algebraic. At the International Congress of Mathematicians held in Paris in 1900, Hilbert asked the seventh of his 23 outstanding unsolved problems whether alpha to the power of beta is transcendental for any algebraic alpha is not equals to 0, 1, and any algebraic irrational beta. Göttingen has speculated that the resolution of the problem lay farther in the future than a proof of Fermat's last theorem, and that no one present in the lecture hall would live to see it successfully concluded. Modern progress has been more rapid than Hilbert anticipated, for the desired transcendence was established independently and by different methods in 1934 by A.O. Gelfond in Russia and T. Snellender in Germany. Snyder. Such number as e to the power of e, pi to the power of e, and 2 to the power of e, and pi to the power of pi, and 2 pi have not yet classified as algebraic transcendental. In 1853, the Englishman William Shank used the infinite series for the arctangent function. Arctan x is equals to x minus x to the forward of 3 over 3 plus x 5 to the power of 5. Absolute x is less than 1, less than equal 1. Together with the formula pi is equals to 16 arctan times 1/5 minus 4 arctan times the 1 over 239. Hand calculated by the first 607 purported digits in the decimal expansions of pi. By 1874 had worked out the total of 707 digits. 70 years the approximation stood as accepted the decimal value of pi. The error in shank evaluations was not caught until 1945 when it was observed that his expansion of pi for phi seemed to disfavor in the 7 digit. This is 7 appeared noticeable less frequently than did any of the other 9 digits. A check on his accuracy revealed erroneous figures from the 528 decimal place onward. The 528 digit should be 4, but Chang called it 5. The decimal representation had been extended to 1120 correct digit using a desk calculator. The first such determination in 1949 produced 2037 digits in 70 hours elapsed time. By 1961, at least 100,000 decimal places were available. A million decimal figures were reached in 1973, where a calculation that required only 24 hours running time, and by 1987, the 100 million digit mark was passed in roughly a day and a half of work. A value of pi correct to 20 decimal place is sufficient for any imaginable application. The latest feat carried the approximation of pi beyond the 50 billion digit bar of the continuum hypothesis. In the paper, a contribution on manifold theory submitted to Krell's journal in 1877 and published the following year. He showed that the point in a square clearly two-dimensional can put in one-to-one correspondence with the point of straight line segment, clearly one-dimensional. Cantor himself found the result so odd that he wrote to the decline. I see it, but I don't believe it, and asked his friend to check the details of the proof because immediately that Cantor's one-to-one mapping was not continuous, he did not read the same significance into Cantor's counterintuitive discovery that Cantor. To establish that the unit square is defined by 0 less than equal x less than equal 1 and 0 less than equal y and less than equal 1, and the interval 0 1 are equivalent, it's sufficient to match their points in one-to-one fashion. Given a point xy of S, let us represent x and y as infinite decimal. We have x is equals to 0 point x sub 1, x sub 2, x sub 3, and so on, and y is equals to 0 point y sub 1, y sub 2, y sub 3, and so on. Of a number z in the interval 0 less than equal to z less than equal to 1, conversely, a knowledge of the decimal expansion of z permit us to reconstruct x and y by enlancing the digit of z. So that transition from z back to x and y can be accomplished by the alternating the block when formatting the decimal expansion of x and y. Thus, for instance, z is equals to 0 point absolute 7, absolute of 3, absolute of 0, 0, 9, and absolute 4, and absolute of 0, 6. We paired would be paired with the point of the square having x is equals to 0.2034 and so on, and y is equals to 0.70060906 and so on. The set of points in the unit square has cardinal number C. Let alpha and beta be two given cardinal A and B with set with alpha is equals to A and beta is equals to B. We write A alpha less than equal B if there exists a one-to-one mapping from A into B. We also write alpha less than beta if alpha is less than equal beta, but not alpha is equals to beta. A less than equal B, where A is the subset of B, because if A is a subset of B, then the inclusion mapping I is equals to A to B defined by A times defined by I times A is equals to A is 1 to 1, so that we have A is less than equal B. Cantor showed, in fact, that whereas algebraic numbers are countable, the transcendental number have cardinal C, the power of the continuum, because every transcendental number is irrational. The irrational numbers must then also have cardinality C. For using T and I to denote the set of transcendental numbers and irrational numbers, we have a chain set of inclusion T subset of I subset of R. These lead to a corresponding inequality involving the cardinal C is equals to T is equals to less than equal I less than equal R is equals to C. There is no alternative but including I is equals to C. The inequality Aleph sub 0 is equals to C. Uh, Inequality Aleph 0 is less than C raises the equation whether there are many sets with cardinality between Aleph 0 and C. On the face of the in the face of the matter, there seems no reason why some uncountable set should not have cardinality less than C. Yet all attempts to discover set of real numbers that is infinite and uncountable, but those power is less than that it continuum have been unsuccessful. The conjectures that there is no cardinality number alpha satisfy Aleph 0 less than A is equal less than C is customarily known as continuum hypothesis. Every infinite subset of R has cardinal number either Aleph 0 or C. Cantor's emotional breakdown in 1844 was caused by strain of his prolonged, futile effort to find a set desired intermediate cardinality. First, he thought that he had succeeded in proving the continuum hypothesis was true. The next day, he asserted that he could demonstrate its falsehood. In the end, an embarrassed Cantor must have seen to all purported proof of these intransigent hypotheses were invalid. Hilbert delivered his famous address in 1900 on astounding problems awaiting solution by future mathematicians. The continuum hypothesis headed the list. Yet, for decades, the question eluded all efforts resolution, and it is today settled in unlocked for sense. Kurt Gödel announced in 1938 to 1939 and published in 1940 that the continuum hypothesis was consistent with the current axiom set theory and hence could not be disapproved. Thus, on the basis of our present understanding of sets, Cantor's conjectures remains in a sort of limbo, as in undecidable statement. It is ironic that specific a pros in Hilbert's list that problem as ambitious program put forward in such a spirit of optimism should have its status changed from unknown to unknowable. Next, we have the paradoxes of set theory. About 1900s, just when Cantor's ideas were beginning to gain acceptance, a series of entirely unexpected logical contradictions were discovered in the figures of the theory of set. Curiously, these were at first called the paradoxes rather than contradiction, and regarded as little more than mathematical oddities. In 1902, the British philosopher, mathematician, and social reformer Bertrand Russell offered paradox in which Cantor's very definition said seemed to lead the contradiction. The modern paradoxes appears in Russell's Principles of Mathematics, published in 1903. Russell paradoxes quite simple, simply using the bare notation of set and elements. If one naively accept the Cantorian view that every condition determines a set, then it obviously possible to consider the set of all set that have property of not being elements of themselves. That is the set. S is the set of A is the set of is a set and A is not the element of A. Symbol not not element standing for the phrase does not belong. The use of E to denote the membership was initiated by Piano in his Arithmetices Principia in 1989, and it is abbreviation for the Greek word meaning is. S itself is a set, so that by the law of excluded middle which says that every proposition is either true or false, S is the element of S, or S is not the element of S, is a true assertion. For S is the element of S, it is follows by S must be one of the sets A, described in the condition, hence S is the element of S as an impossible situation. If S is the element of S, then S satisfies the property by which one determines which sets are element of S. Thus, S is not the element of S, which is equally began to total. The elder statesman of French mathematics, Henri Poincaré, who had little faith in mathematical logic, was overjoyed that the careful constructed logical foundation was insufficient to bear the weight arithmetic. He exclaimed, "It is no longer sterile, it begets contradictions." This may also have been a play on the saying logic is barren, where mathematics is the most prolific mother. The earlier of paradoxes, one based of the consideration of the set of all ordinal numbers, was published in 1897 by the Italian mathematician Cesare Burali-Forti and known to Cantor at least 2 years earlier. In 1899, Cantor discovered a paradox that had to do with his theory of cardinal number. This was based on other far-reaching theorem of his 1833, which said that for any set A is power set had a larger cardinal number than that of A. By the power set of A was meant the set of all subset of A. Our notation for the powers of A is a power set of A. For any set A, there does not exist a function mapping for onto power set. Proof. The general plan of attack is to show by an indirect argument that no such function exists. Therefore, we start with the assumption to be refuted in the end that there is a function f is equals to power set of A that is onto power set of A. This means that to each element A is the element of A, there is assigned a subset A FA of A. Let us consider the set B defined by B is equals to the set of A, element of A. A is not the element of FA. The set B is a subset of A, so that B is equals to FB for some B element of A. We call that F map onto power of set A. We now ask innocent question: is the element B a member of the set B? If B is the element of B, then by the very definition of the set B, we have B is not the element of F, B is equals to B, which is impossible. On the other hand, B is the element of B is equals to FB, implies that B satisfies the defining property of B, so B is the element of B. This is also nonsense. It follows that no function f as described here can exist, and the proof of the theorem hereby concluded. For any set A is less than power set of A. We must show first that A is the not we must show first that A is less than power set of A, and then that A is not equal to the power set of A. The meaning of the statement A is less than equal to the power of A is that A is the equivalent of a subset of power set of A. That is there exists one-to-one correspondence between A and a subset of power set of A. Quite obvious that the function that takes a element of A onto single element set A in the power set of A defines such correspondence. For the task of proving that A is not equal to power element of A power set of A, it is enough to show that there is no one-to-one correspondence between A and the power set of A, because such correspondence would certainly be a mapping of onto power set of A. It cannot exist by Freebu's theorem. This gives the desired conclusion. For in the special case in a cardinal number C, then the theorem indicates that C is equals to R less than power set of R by interacting the operations of forming the power set and an ending hierarchy of infinite cardinal can be obtained. A paradox arises when we consider the most comprehensive of all sets, the set U can be contain all the sets or the union. By Cantor's theorem, P is the set of U is greater than U, because U is the set of all set, where power set of U is a set, the elements of which happen to be the subset of U. Power element of U is contained in U. Hence, power element of U is greater as less than equal U, and we have contradicted. Loud voices in France reached such proportion that at the International Congress mathematician held in Rome in 1808, the eminent Henry Poincaré, who was regarded as something of an oracle in mathematics, we went so far as to say later mathematicians will regard set theories as a disease from which one has recovered. Russell paradoxes showed without any consideration involving cardinal numbers that one cannot allow arbitrary conditions to determine sets and then indiscriminately permit the set so formed to be member of other set. Each of the various solutions proposes that proves to be successful lay the blame on the introduction of sets were excessively large. Thus, an essential ingredient in any formal theory of set was to be an action guaranteeing a limitation of size. Next, we have the Zermelo and the action of choice. The first successful axiom treated of set theory was published by the German mathematician Ernest Zermelo in 1908. Zermelo, who received a doctorate from University of Berlin in 1894 with a dissertation on the calculus of variation, began his career not in set theory, but in mathematical physics. The following year, 1901, he published his first relevant paper consisting of the several results in the arithmetic of cardinal numbers in a famous memoir, Foundation of General Manifold Theory, in 1883. Cantor stated that every well-defined set can be brought into the form of a well-ordered set. Zermelo supplied the cardinal proof of the well-ordering theorem in 1904, a proof that unleashed much spirited controversy. The The action of choice, a name given by Zermelo, asserted that from any given collections of disjoints non-empty sets, it would be possible to choose exactly one element from each set, thereby form a new set. The controversy touched off by the action of choice remind one of another famous axiom, Euclid's parallel postulate. Emile Barrel insisted any argument where one supposed an arbitrary choice to be made an uncountably infinite number of times is outside the domain of mathematics. Another such mathematician, Jacques Hadamard, crystallized the whole controversy into the question: can the existence of mathematical entity be proved without defining it? The original axioms of Zermelo is amended by Frankel, von Neumann, and others are now called the Zermelo-Frankel axiom for set theory. He observed that all mathematicians would not normally think of using such set as the set of all sets, or the sets of all sets which are not the elements of themselves. Thus, Zermelo formulated principle by which guaranteed the existence of certain subsets. To every set A and every defined property Px will correspond a set whose elements are exactly those elements X in A for which properly P is the set of X holds. The Vogue notations of definite property gave rise to misgiving almost from the outmost. The idea was made more precise by Franklin 1922 and somewhat differently by Skolem in 1922 to 1923. The restrictions implied by Zermelo's axiomatization avert the disasters of the paradoxes because the critical set that appears in Russell paradox, the set of all sets which are not elements of themselves, cannot be formed in Zermelo's formula set of theory. The best one can do is to produce the set. S is the set of A, element of A is that A is the set of A and A is not the element of A. Where A is the set of A, all of sets known to exist. Zarmelo Franklin's axioms turned out to be a blind alley. According to Gödel's famous incompleteness theorem, it is impossible in a certain system to prove consistency. Cohen in 1963 succeeded in showing that the negation of both the axioms of choice and continuum hypothesis is also consistent with the rest of the Zarmelos axiom system. And we have the logistic school, Frege, Piano, and Russell. The paradoxes of the infinite led to the stage for a modern crisis in the foundation, unlike the profound disturbing situation that arose when the Pythagoreans unexpectedly discovered incommensurable quantities. It appeared to many that the entire structures of mathematics was weak, or at least built on weak foundation. In early 1900s, widely different diagnoses of the ills of mathematics divided mathematicians into various camps. The three main schools of thought concerning the nature of mathematics are usually distinguished as the logistic, also called the logistic, formalist, and intuitionistic school, and their base known proponents identified as Bertrand Russell, David Hilbert, and L.E.J. Brewer, respectively. Logic was not simply an instrument in the constructions of mathematical theories. Mathematics now became the offspring of pure logic. According to the logistic philosophy, all mathematics concepts must be given definition only from ideas that are part of logic, and all mathematics statements must be deducible from universally recognized assumption of logic. Logic is as much in need of definition as mathematics is. The first determined effort to rewrite the established body of mathematics in logical symbolism was made by German logician philosopher Gottlob Frege. Frege received his doctorate in mathematics from Göttingen in 1873. His small but weighty treatise entitled Begriffsschrift, Begriffsschrift einer der arithmetischen Nachgebildel Formelsprach des reinen Denkens or conceptual notation, a symbolic language of pure thought modeled on the language of arithmetic. Published in 1879, was a natural milestone of history in modern logic. In Begrish thrift, the whole calculus of proposition and the device known as quantification theory was presented for the first time. In two principal works, he chosen the arithmetic of his subject, the foundation of arithmetic, which appeared in 1884, and Grand Cedar arithmetic or foundation or fundamental law of arithmetic, of which volume 1 was published in 1893 and volume 2 in 1903. Owing to the complexity of the symbolism, a monstrous waste of peace, said one critic, and the novelty of the approach. This writing passed almost wholly without recognizing until Russell devoted an appendix to them in the Principles of Mathematics in 1903. Another great pioneer in the study of this foundation mathematics and a master of art reasoning formal logic was the Italian mathematician Giuseppe Piano. Piano's first attempt at deducing the truth mathematics from pure logic was his Arithmeticis Principia Nova Metodo Exposita of 1889, a small tract of 29 pages written almost entirely in the symbol of that he called mathematical logic. Among the body of signs Piano invented for these were elements belong to and logical sum or union, and the logical product of intersection, and the logical implies or the contains. The horseshoe symbol became the standard notation for the material implication after Whitehead and Russell used it in their Principia Mathematica. The Arithmetices Principia is noteworthy for containing the first statement of the famous postulate for the natural numbers, perhaps the known for Piano's achievement. This was carried out in the Formulaire de Mathematiques, which expresses in the symbols all known definitions, proof and theorems, and extensive tracts of mathematics. In the Principles of Mathematics, which contain the first explanation of the paradox that bears his name, Russell put forward the opinion that logic is progenitor of mathematics. The present work has fulfilled two objects. First, to show that all mathematics follows from the symbol logic, and secondly, to discover as far as possible what are the principles of symbols logic itself. The proposed second volume never came out because the reversion of material necessitated writing a wholly New York the Principia Mathematica. The apex of the logistic conception of mathematics is Principia Mathematica, written by Russell in collaboration with his first and older colleague, Alfred North Whitehead. A massive work of bewildering complexity, its three-volume comprise more than 200 pages. Taken as a whole, the Principia constituted a formidable effort to prove the logistic thesis that mathematics has in this indistinguishable from logic. To ensure strict observance of the various circle principle, he introduced his theory of logic types. This idea made set theory secure against illegitimate totalities, but it led to the difficulties in the body of mathematics itself. Many important theorems not only could not be proved but could be even expressed. Among them was Cantor's theorem that there are more real numbers than positive integers. Adherence to Russell rules of hierarchies introduced completion in Dedekind's theory of real line. Russell overcame these weaknesses by positing a new axiom, which he called the axiom of reducibility. The axiom is less part of the deductive system of logic than the rule for manipulation symbols. The sole justification for the axiom of reducibility was that there seems to be of no other way out of the particular difficulties en, uh, enge- engendered by the theory of types. It became the main bone of contentions for the critics of the system of the Principia. One critic stated that the introductions to the axiom incredibility into the Principia without any supporting reason was an act harakiri. But he could find no satisfactory alternative in his attempt to draft from the second edition 1925 of the Principia. The preparations of a fourth volume of the Principia on the logic foundations of geometry, which was to be written largely by Whitehead, interrupted by World War I, at a time when pacifism aroused bitter emotions. Oppositions to the war caused him to denounce unpatriotic. As the author of Principia moved on to this new territory, the leadership in research into the foundations of mathematics passed to the German authority David Hilbert. Next, we have the Hilbert's formalistic approach. Hilbert's interest in foundation dated to this investigation of geometry in the 1890s. The question that Hilbert explicitly formulated the first time was consistence of his sets of axioms. There should be no paradox or contradictions consisting of two theorems, one of which could be negations to the other. As a natural evolutions of this work, the Second International Congress of Mathematics in 1900s, he offered as one of his list of the most challenging current problems that of consistency of the actions of arithmetic. But at the time of the Third International Congress, which was held at the Heidelberg in 1904, the emergence of paradoxes had brought mathematicians onto uncertainty. Hilbert, speaking before those gathered at Heidelberg, volunteered his service in the reconstructions of mathematics. Hilbert did not act on his Heidelberg proposal for many years. Instead, he became absorbed first in the integral equations and then later mathematical physicist. One of the fundamental canons of this thinking that the analysis of Weierstrass and the concept of infinity as it appeared in the working of Cantors were built on sand. Thus, to salvage traditional mathematics in the face of Brewer's attacks, Hilbert proposed a bold new program. It requires first that the whole of existing mathematics, including logic, should be axiomatized, and second, that is axiomatic theory should then be proved consistent by simple unitary argument. This approach to foundation became known formalism. Before Hilbert's proposal, the method used in consistency proof for an axiomatic theory was merely to lift the burden to another area of mathematics. As a step toward carrying out such program, Hilbert introduced the notions of formal theory, a completely symbolic axioms theory in which there was explicitly incorporated a system of logic. Hilbert's idea was the axiomatic development pushed to its extrema. Hilbert denied, however, that logic was more than mathematics and should precede it. Particularly help in symbolizing the statements of mathematical was the Principia of Russell and Whitehead, which Hilbert called the crowning achievement of the work axiomatization, for by actually exhibiting the details, the Principia showed that all mathematical statements could be translated into a small body of symbol that the law reasoning reduced to several simple rules of combining this symbol. A formal theory, as set up by Hilbert, starts with a stock of symbols and the rules governing them. Mathematics for Hilbert became purely formal calculus and almost mechanical manipulations of symbols devoid of concrete content. During the decade 1920s to 1930, Hilbert, his two young assistants, Wilhelm Ackermann and Paul Benes, worked diligently to carry through the objectives of the formalist program. But such optimistic expectations were dealt a staggering setback when Kurt Gödel, a 25-year-old mathem, the University of Vienna, announced an important and dismaying discovery. Gödel proved his result in 1930. An abstract was published at the end of the year, and the full details appeared in early 1931. Hilbert originally intended to prove the consistence of a formal system, such mean as could be formalized the system itself. Gödel showed this program to be incapable of fulfillment. According to Gödel, this consistency of formal systems strong enough to be considered a foundation of mathematics could not be established from within the system by strictly finitary method. Thus, either the system one was inconsistent to begin with or it consistent. The limitations prescribed by Hilbert's were inadequate to formalize a proof of its consistency. This melancholy revolution effectively brought to an end the initial phase of the tonalistic movement, Brouwer's intuitionism. While Hilbert's proposed to save and safeguard the customary formulations of mathematics by a consistency proof, the Dutch mathematician L.E.J. Brouwers was ready to practice those parts of the subject in which he left that language had outrun clear meaning. It was Brouwer's intuition to develop an intuitionistic mathematics using only those constructions that had a clearly intuitive justification. Brouwer had a rare insight into the defects of classical mathematica, the familiar mathematica using the logic of Aristotle, and he had a valiant attempt to set things right, begin in 1907 with his doctoral dissertation. The dissertation, entitled On the Foundation of Mathematics, was a penetrating criticism, direct against Cantor, transfinite numbers, against the logicism of Russell, against Hilbert, axiomatic method. This was followed in 1912 by Intuitionism and Formalism, a memoir that consolidated Brewer's program. Two articles of faith emerged: the reduction of mathematics to the ultimate intuition of the natural numbers, and the rejections of the unrestricted applications of the law of the excluded middle. Another no less important feature of the intuitionistic position was its challenge to the logistic presumptions of the priority of the logic over mathematics, where Frege, Peano, and Russell's thought a logic symbolism was prerequisite for mathematical knowledge. The intuitionists repudiated any such requirement. Brouwers in his dissertations argued that mathematics was a mental construction, a free creation of mind, complete independent of language and logic. Symbolic, symbolic logic does not represent an essential features mathematical reasoning, and by its can never create any mathematics. The symbol language must not be confused with mathematics in conveys it reflects but does not contain mathematics reality. He upbraided the formalists of building self-subsistent verbal edifices that could be studied apart from any intuitive interpretation. To that extent, they reduce mathematics to a meaningless game of formula. What the formalist school, seems to have overlooked is that between the perfections of mathematical language and the perfection mathematics proper, no clear connections can be seen. Brouwer's conceptions of mathematics had some affinity to the conceptions of Immanuel Kant, both mending the source of mathematical truth in intuition. Brouwer maintained that the common belief in the applicability of classical logic to mathematics could only be considered a phenomenon of the history of civilization of the same order as the old-time belief in rationality of. According to his interpretation, traditional logic arose from the mathematics of the finites and their subsets. Then, forgetful of his limited origin, people mistook that logic for some had an priority existence independence of mathematics, and finally they unjustified applied it by virtue of its priority character to the mathematics of infinite sets. A specific example of a logic principle valid in reasoning with finite set that Breuer's rejected for infinite set was the of the excluded middle. The, the supposition underlying this principle is that each mathematical statement is determinably by true or false, independence of the means and available to us of recognizing its truth value. For Brewer, purely hypothetical truth values were an illusion because it could be guaranteed beforehand that such construction could be found. We should have no rights assume of each statement that it is either true or false. For instance, Brewer asked whether it is true or false that in the decimal expansion of pi there occur the successive digits forming a sequence of 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. This would evidently require that either indicate the sequence of 0, 1, 2, 3, 4, 5, 6, 7, and 9 in pi, or demonstrate that no such sequence could appear and no method existed from making the decision. So, one could not apply the law of excluded middle here to include that statement could have be either true or false. On the other hand, it is legitimate from the intuitionist standpoint to assert that the number 10 to the power of 10 to the power of 10 plus 1 is neither prime or a composite without being able to say which alternative actually holds. There is a method of one were to take the trouble to apply it. It is effective for deciding which alternative is correct. Brewer's criticism of the logic used the classical reasoning arose from his refusal to accept not constructive existent proofs. This is proofs that establish the existence of something without proving an effective means for finding it. Giving a non-constructive existence proof observed, observed well is like informing the world that somewhere there is a buried treasure but not saying where it is. The intuition regarded the idea that there might exist a set could be constructed as a piece of hopeless, confused metaphysics by refusing to define a set to define a set by means of an attribute characteristic of its element and limiting themselves to constructive methods. Brewer's followers did away with the problem raised by the paradoxes set of theory. The abandon of the law of the excluded middle and with non-constructive existent proof was too radical a step for Hilbert to accept. Each of these schools of thought contains serious defect and none achieved its objective of proving a universally acceptable approach to mathematics. Today, foundations of mathematics is not a field in which same intense actively takes place secures in the early part of the century. Despite the indecisive outcome of the original undertaking, the work done by the three schools had one great value. It revealed the extreme subtlety and complexity of the interplay between logic and mathematics. And that's all. Thank you for watching and listening.